3 years probably, but it's almost done.
That's exciting. Are you near campus?
Yeah.
Cool.
So they had a light rail station on one side of campus. Now they're extending the line, and this is the stop on the other side of campus.
Is that the line that kind of goes north-south? I think I've taken that to campus, and then it kind of stops like at the University of Washington stop.
Yeah. So yeah. So this is just the next stop down the line. They're adding 3 more opening next year sometime.
That's awesome. Good news. Welcome, everyone. We'll get started in a few minutes. All right, Rob, are you ready to get started?
Yeah.
Cool. Welcome, everyone. Good morning. Very happy to introduce Dr. Rob Jnglin Wills as our seminar speaker today. Dr. Jnglin Wills is a postdoctoral researcher in the Department of Atmospheric Sciences at the University of Washington. He received his bachelor's in engineering physics from UC Berkeley in 2011 and his master's and PhD from Caltech in 2016. After a postdoc at ETH Zurich, he joined University of Washington in 2017. He also recently received the University of Washington Data Science Postdoc Fellowship in 2019. His research interests include climate dynamics, large-scale circulation of the atmosphere and oceans, climate variability, and Earth system modeling. Today, he will speak about slow modes of global temperature variability in regions of weak radiative feedbacks. So take it away, Rob. The floor is yours and your slides look good.
Thanks, Katie, for the introduction and for the invitation to speak to you all at NCAR. So kind of have 2 titles here. The first is a bit more descriptive of what I'm going to be showing. I'm going to be looking at decadal variability of Earth's energy balance in CMIP6 in particular. But then the title that I submitted is a bit of a subtitle to this that highlights one of the main physical conclusion, that slow modes of global temperature variability primarily occur in regions of weak radiative feedbacks. And my cat is trying to say hello already. So this is work in collaboration with Kyler Moore and David Battisti at the University of Washington, as well as Christy Poisescu and Luke Parsons. So first, I want to give you a bit of an outline. I'm going to start by talking about some of the open questions I want to address about the role of decadal variability in global climate. Then I'm going to introduce some of the CMIP6 simulations and the decadal variability in global mean surface temperature in those simulations before breaking this up into different modes of low frequency variability and talking about their individual impacts on global climate. Then I'll talk about a bit of the why behind that by looking into some of the particular radiative feedbacks that are engaged by these different modes of low frequency variability. Then finally, at the end, I'll talk a bit about how this influences estimates of climate sensitivity from short observational periods. So one of the big motivating questions here, and that has motivated a lot of work on decadal variability, is what causes variability in the rate of global warming. So if you can roughly see some periods in here where there's more greater global warming or less, such as this so-called global warming hiatus, which doesn't really look like much here, but got a lot of attention when it was going on, because it occurred kind of a critical time in discussions about climate. So some of this, a lot of this is due to internal variability. And in this way, this is obscuring the forced response. But this internal variability also offers an opportunity to understand the climate system. So I want to understand some of the reasons for these changes in the rate of global warming over time. And if you look in particular at this, or something similar to this period, minus the period just before this, you see a rather unusual pattern of global temperature change with this pattern of cooling and this horseshoe-shaped pattern of cooling in the Northeast Pacific and into the tropical Pacific. So this is very much not a uniform rate of warming over this time period. So one of the questions I'll be getting into here is how has decadal internal variability, or how can it contribute to this pattern and rate of observed warming? And I want to introduce some of the main players here. One is the Pacific Decadal Oscillation, which has a pattern that looks quite a bit like the pattern I just showed, with a pattern of this horseshoe-shaped pattern of warming and cooling in the North Pacific. And this is a mode of variability that's just normally defined as the first EUF of these North Pacific SSTs over this box. And it's been pointed out by a number of studies here from Trenberth 2015 that the different phases of the PDO correspond roughly to these different breaks in the global rate of global warming. So with positive PDO phase corresponding to accelerated warming and negative PDO corresponding to less warming. But there's also been some other work suggesting that the Atlantic could play a role in this, partially because tropical Atlantic variability has teleconnections through tropical convection into the Eastern Pacific. So these basins are not completely independent of each other, but because the Atlantic evolves on a long time scale with what's called the Atlantic multi-decadal oscillation, which is typically defined by this large-scale SST average over the North Atlantic. This has been suggested to be playing a role on the longest time scales in modulating global temperature. One other aspect of the problem I want to talk about is how Earth's energy balance changes in response to these modes of variability, because Earth's energy balance is really critical for determining how the climate system responds to radiative forcing in the long term. So here's a schematic from Trenberth et al. 2009 of the global energy balance. Here I'm really just going to be talking about kind of the basic picture of this, where it's a linearization of the global top of atmosphere energy budget, where basically you're trying to look at anomalies in the top of atmosphere energy balance in terms of a radiative forcing and a response to that radiative forcing that depends linearly on global mean temperature with some feedback parameter lambda. This is the basis for defining the often discussed equilibrium climate sensitivity, which is just the radiative forcing of a doubling of CO2 divided by lambda. So it's basically the temperature you get once this radiative TOA radiation anomaly goes to 0. And there's been some studies that have used this framework to try to constrain the future climate response from observations. So basically what this involves is it involves looking at the change in temperature in some period relative to some pre-industrial state, and the change in radiation over that same period relative to that pre-industrial state. And then you can make an approximation of this equilibrium climate sensitivity by looking at the change in the radiative response in the denominator and the change in global temperature in the numerator here, and then just plugging in the radiative forcing that you'd get from a doubling of CO2. And so this Otto et al. 2013 paper did that and found these kind of ellipse constraints for what ECS should be. So I relabeled this inferred climate sensitivity here because there ends up being some differences between what you'd expect for a transient warming and a long-term warming. And this a difference I'm not going to get a lot into here, but the field is now calling this an inferred climate sensitivity if you infer it from an observational period. And the observational estimate from Otto et al. Has this PDF like this in terms of ICS. And if you compare this to ECS of climate models, it's this observational estimate is quite a bit lower. So this raised a lot of interest in this because this is suggesting that climate sensitivity isn't as high as the models are suggesting. But there's a number of reasons for this discrepancy that I'll get into a little bit. There's been a lot of work on this recently. So the main reason for the difference in climate sensitivity between this observational period and the long-term warming is differences in the SST pattern. One aspect of that is that observational SST patterns change does not look like the modeled trend over the same time period. And if you just plug in the observed trend, so using fixed SST simulations, ANIP simulations, you see that a lot of this discrepancy gets rectified, where the same model with fully coupled has a higher climate sensitivity than that model does when it's forced by these SSTs. So a big part of this discrepancy between the inferred climate sensitivity and long-term climate sensitivity is that this observational period had a very strange SST pattern. So same as was relevant for this change in the rate of global warming. And there's a lot of hypotheses out there for what has caused this weird SST pattern. Some are multidecadal internal variability, as I've already discussed, Pacific multidecadal variability or Atlantic multidecadal variability. But there's also hypotheses that this is due to a bias in the forced response, due to models having a biased climatology in the tropical Pacific or an incorrect response to aerosol forcing. And distinguishing between these two forced and unforced mechanisms, particularly for this pattern of tropical Pacific SST change, is critical for both for validating models and for understanding what pattern of warming we should expect in the future, as well as just for knowing how much multidecadal variability there really is in the climate system, which is important for decadal and longer timescale climate projections. So I'm going to be looking in particular into the internal variability aspect of this, looking at how much of this spread in ICS or this discrepancy in ICS could be just due to internal variability, and how much internal variability can lead to variability in global mean temperature. So what I'm doing here is I'm breaking up this inferred climate sensitivity formula into a forced and unforced component. This plot here just shows what you can see if you just look at different large ensemble members from the CSM1 large ensemble and look at its inferred climate sensitivity in each model. So this plot shows a few different things. One is that the internal variability does lead to quite a large spread in inferred climate sensitivity. The other is that the mean of this distribution is lower than the ECS of the same model. So this is due to the pattern effect in the long-term transient climate response, which I'm not going to talk about more here. And another is that none of the, another thing you can notice is that none of the CESM1 large ensemble members have anywhere close to as low of an ICS as CAM5 does when forced with observational SSTs. So none of the coupled simulations are having as weak of radiative feedbacks as the historical SSTs would imply. And a lot of this spread in ICS is just determined by the rate of warming over this time period. So there is some interdependence of the ICS spread on the spread in the rate of warming. So these are the two main quantities I'm going to be discussing here. This is also true across some other CMIP6 models. So there is, in general, this relationship between the ICS within a particular simulation and its rate of warming over this historical time period. So the main questions I'll be getting into here are what causes the variability in the rate of warming across different ensemble members or different models, and how does the pattern of observed warming influence the global energy budget and therefore the inferred climate sensitivity. So that was kind of an extended introduction, so I just want to kind of wrap up where I'm going with the rest of this talk. And the two main questions I'll be talking about are how can decadal internal variability contribute to changes in the pattern and rate of global warming? And how does this internal variability influence estimates of climate sensitivity by changing the global energy budget? So first, I'm just going to be talking about the decadal variability in global mean surface temperature within CMIP6, just to kind of introduce the CMIP6 simulations I'll be looking at and show how much variability they have in global mean surface temperature. And this is from recently published work, which was led by Luke Parsons. So what I'm showing here is the time series of global mean surface temperature in observations on top, with including the forced trend. So this is similar to this staircase-like global mean surface temperature rise that I showed in the introduction. Then below this, I've shown on the same scale the global mean surface temperature variability in 9 different CMIP6 pre-industrial control runs. And in the 3 of these with the most global mean surface temperature variability on interdecadal timescales, this variability in global mean surface temperature, or I'm going to be referring to that as GMST for short, is almost as large as in observations. But there's quite a range of the interdecadal GMST variability between different models, and some other models have very little on decadal and longer timescales. You can visualize this also in terms of kind of a histogram of GMST variability on decadal and longer timescales for pre-industrial control simulations compared to historical. So for CMIP6, which are the green ones here, the pre-industrial control runs, some of the ones with the most variability can have almost as much or more variability than some of the historical simulations from other models. And they're actually getting close to the interdecadal variability in global temperature from instrumental data, which includes the full forced trend. So there's really huge global mean surface temperature variability in these pre-industrial control simulations, which is just from internal variability. There's no forcing in these simulations. And so if you look at the regions that are coherent with this global mean surface temperature variability, it's in very different regions in different models. So taking here 2 of the most variable models, that's either coming from the whole Northern Hemisphere with a bit of focus in the Arctic and North Atlantic, or from the Southern Ocean. Other models with a little bit less variability show that global mean surface temperature variability is coherent with the tropical Pacific, or others don't really show a main region of variability that's coherent with this GMST variability. While I'm showing these results, I should mention that just because these pre-industrial control simulations don't show so much unforced GMST variability doesn't mean that this is a way to interpret the observations. the spatial pattern of coherence with this global variability is quite different. In CMIP6, you don't really have any one region that dominates the, or you really don't have any one region that's very coherent with this global mean temperature variability. The region that's most coherent is the high latitudes. Versus if you look at historical simulations or instrumental data, you see the strong coherence of the tropics, in particular tropical deep convective regions with global mean surface temperature variability. So this is really a signature of forcing in the instrumental data that really doesn't show up in these pre-industrial control simulations. So this tells you that, okay, internal variability can account for a lot of global mean surface temperature variability, but it motivates an additional question: is what type of internal variability is really causing such large interdecadal swings in global mean surface temperature without any radiative forcing? So then I'm going to jump into the next part where I kind of break this down into different types of internal variability. The tool I'm going to be using to do this is called low frequency component analysis. And this is a tool I've been using for kind of a series of recent work on different modes of low frequency variability in the climate system and their physical mechanisms. What it does is it finds SST patterns with the maximum ratio of low frequency to high frequency variance, where low frequency here is defined as decadal and longer timescales. And I'm going to be calling these the patterns it finds low frequency patterns. They're basically linear combinations of EOFs that highlight the slow processes in the climate system. And while a low pass filter is used to find these patterns, the data is not explicitly low pass filtered. So this makes it good for determining the relationships of these modes of variability with higher frequency physical mechanisms. And I'm going to be looking at particular 35 different CMIP6 pre-industrial control simulations with 400 years of deseasonalized monthly mean SST anomalies from each model. But I'll note, and I guess show one example, that this gets qualitatively similar answers when applied to models individually. Just want to give a brief, more technical description of how this method works for those who are interested. Basically, you take your data matrix, so a matrix of SST anomalies as a function of space and time. And first, you just compute a regular principal component analysis to get your EOFs. Then you apply a low pass filter to your data. So with a cutoff timescale, I'm using 10 years here. Then you input both the original full data matrix as well as the filtered data matrix into a low frequency component analysis, where you project each of these onto your EOFs and find the linear combination of EOFs that maximize the ratio of low frequency to total variance. So this is the ratio of their projection onto the filtered data divided by their projection onto the unfiltered data. And this turns out to be a linear algebra problem that you can solve exactly. And what that gets in the end, once you project this back onto the full data matrix, are low frequency components that are analogous to principal components, but are focused on this low frequency variability. And their SST, or their anomaly patterns, in this case SST, which I call low frequency patterns. And please feel free to send questions along at any point during the talk if you have any clarifying questions. Didn't actually hear what the normal way of doing that in your seminars are, but I'm happy to be interrupted with questions if there are any clarifying questions. So want to jump into the results now. So these are the low frequency patterns I'm going to be showing you of the CMIP6 pre-industrial control simulations. It's a composite over all 35 different models. The first low frequency pattern is a pattern of mostly Atlantic multidecadal variability focused in the Atlantic subpolar gyre. And this is highly coherent with the traditional AMV index on decadal and longer timescales. So it's really capturing the decadal variability of the AMV, which is of course what the AMV is intended to do in the first place. But the traditional AMV index does mix in some higher frequency variability that differs in its phasing with this variability. And something similar to this index, but defined just based on Atlantic SSTs, although it gets almost the same answer, was used in a recent paper of mine to establish the role of AMOC in the AMV. Of course, this is an idea that goes back a long time, but there's been a lot of debate on this. So I hope that this paper made some progress in settling that debate at least. And what we find there is that this AMOC and AMV variability is a delayed response to positive NAO anomalies. Just giving you kind of a brief picture of the mechanisms of this variability, because I'm not going to get into them more in this talk in particular. I'm also not going to be talking a lot about the observations, but I do want to mention that you can find a similar pattern of AMV variability by applying the same method to observations. The second pattern you find is a pattern of Southern Ocean multidecadal variability. And this is strongest in models with variability in open ocean deep convection. And this has been studied in a number of those models individually, and a number of papers referenced here. But here we find that this variability is actually present in basically all models, even ones without a lot of open ocean deep convection. So suggests there might be something more general here. But due to its long time scale, this is really evolving on multi-decadal timescales, it's hard to validate in observations, especially with the sparse observations in the Southern Oceans. But I will say there are hints of this sort of variability in work out of NCAR, Fan et al. 2014, and Sally Zhang's recent work. The third pattern you find is a pattern of Pacific decadal variability. Looks a lot like the PDO. In fact, it's highly coherent with the traditional PDO index at decadal and longer time scales. So again, it's capturing the decadal variability of the PDO. And this was used in another recent paper of mine to look at the role of ocean gyre dynamics in the PDO, kind of showing that this particular decadal variability with this pattern is mostly coming from the ocean gyre dynamics, not, as some other studies have said, primarily due to like wind-driven temperature variability. And this gyre variability does, it results instead of from heat flux-driven variability from a delayed response to Aleutian low wind stress anomalies. And again, you can find a similar pattern if you apply the same method to observations. And while I don't want to discuss them too much more here, I do want to show some of the higher order patterns just to show that they continue to find fairly physical looking things into the higher order patterns. Note here that I did apply an additional rotation to localize these patterns within ocean basins. So the fourth pattern gets a dipole in Southern Ocean temperatures that has been studied in the GFDL model by a paper by Zhang et al. 2017. The fifth pattern gets something similar to the Victoria mode or North Pacific gyre oscillation. And the sixth pattern gets some Atlantic decadal variability linked to the North Atlantic gyre circulation. So just to say that there seems to be some reasonable things coming out of this analysis all the way into the higher order modes. And want to briefly mention how the amplitude of these modes varies across all the different models I'm looking at, particularly because the first two modes are really dominated by a couple models. The Atlantic multidecadal variability is very strong in the models that use the NEMO ocean model. So there's all these blue bars here, CNRM and EC Earth. And the Southern Ocean multidecadal variability is largest in models that use the GFDL MOM ocean model. So that's models like BCC and GFDL CM4. And since this is NCAR, I'll point out that CSM2 here doesn't have particularly strong variability, Atlantic multidecadal variability, or Southern Ocean multidecadal variability, it's a bit weaker than the ensemble mean, the full CMIP6 ensemble mean, but it does have stronger than average Pacific decadal variability captured by the low frequency patterns 3 and 5. And I thought it would be helpful just to show what this looks like applied to an individual model. So CSM2 here. And so the first pattern of Atlantic multidecadal variability looks quite similar to the full CMIP6 ensemble. And this gives you a sense of how it evolves over the pre-industrial control simulation. But the second pattern looks a bit different, and there's a bit more going on in the Northern Hemisphere in this second pattern. But really, you shouldn't be strictly interpreting these as separate modes of variability. If they have similar timescales, this analysis, as any other analysis of spatial temporal variance, can mix to get together different types of variability if they happen with a similar amount of variance on a similar range of timescales. So there is still some Southern Ocean multidecadal variability going on here, but because it has a weak amplitude compared to what's going on in the North Atlantic, it gets kind of mixed together with that. So just a bit of a caveat to this type of analysis. And then the PDO looks fairly similar to the multi-model composite. And then the next two patterns capture this Victoria mode and North Atlantic gyre variability. There's not really the strong Southern Ocean dipole variability that I showed in the other pattern in CSM2. But then I want to get back to this CMIP6 multi-model composite and continue forward with what the main thrust of this talk, which was to look at the impacts of these modes of variability on global climate. So first, I'm just showing the lead lag relationship of each of these first three modes with global mean surface temperature. And what you can see is that the first two modes have a very large and long-lived impact on global mean surface temperature. So 0.03 to 0.05 degrees C per standard deviation in this mode, and persisting for several decades. The PDO, like low frequency pattern 3, doesn't have as large of an impact, as not nearly as long lived. And unlike the symmetric evolution of global mean surface temperature through the AMV and Southern Ocean multidecadal variability events, there's this asymmetric impact on global mean surface temperature where you first have a warming and then a cooling. So the PDO is leading to a reduction in the rate of warming from one decade to the next, which is consistent with existing literature. Then I also want to talk about the impact of these different modes on global mean top of atmosphere energy imbalance. So the first one really has very weak radiative feedbacks. So just a weak negative feedback in the period after your warming. So this is energy loss from the Earth system after your period of warmest temperatures. The radiative anomalies associated with the second pattern are also quite weak, but they do have this positive feedback that's a little bit larger going into lag 0. So this, I'll show a bit later, is the result of positive sea ice albedo feedbacks that act to amplify this Southern Ocean variability leading up to its period of maximum temperatures. And the PDO, consistent with its kind of asymmetric impact on global mean surface temperature, also has an asymmetric, more complex looking evolution of global mean TOA, which is a little bit larger in amplitude, but still quite short in time scale than these other modes. So one way to think about how large these values are is to convert this to an effective global radiative feedback, looking at the period after the radiation has had a chance to respond to this variability. So, so the decade after lag 0 here, I'm going to be looking at the global mean TOA and dividing it by the global mean temperature, turning that into an effective global radiative feedback. So for these first two patterns, this value is very, very small, 0.5 or so watts per meter squared per Kelvin. And if you converted this to a climate sensitivity in response to a doubling of CO2, although of course this is not a response to a doubling of CO2, but just for the sake of converting this to values we're more used to thinking about, this would correspond to a climate sensitivity of 7 to 8 degrees Celsius. A very large climate sensitivity associated with these weak radiative feedbacks. Doing the same analysis with the PDO like LFP3, you get slightly larger effective global radiative feedback, but still quite a large climate sensitivity, about 5 degrees C. Still larger than what we expect for the forced response. In contrast, if you do this same analysis with ENSO as characterized by the Nino 3.4 index and look at its impact on global mean surface temperature and global mean top of atmosphere energy imbalance, and then look at the anomalies in the decade after its a maximum, this gets you a global radiative feedback that's quite a bit larger, 2.2, and this would correspond to a climate sensitivity of something quite low, of about 1.4. So going to show a new figure here, but also kind of just summarize what I've shown so far. These two figures are just showing the coherence of all of these different modes with global mean surface temperature on the top and global mean 2A on the bottom. And this shows a lot of what I've already shown, that the first two patterns, LFC1 and 2, have a large coherence with global mean surface temperature variability at the longest time scales, but they do not have nearly as much coherence with global mean TOA at those time scales. Nino 3.4 is shown here as well, and its impact on global mean surface temperature and global mean TOA is focused on ENSO timescales interannual, so 3 to 7 years or so. But it actually has such a large impact on both that it persists out to decadal and longer timescales. So it is still an important player at these long timescales, even more so that for TOA than for global temperature, just because these other modes don't really matter for TOA very much. So in the next section, what I'm going to get into is why do these different modes have such different impacts on global temperature versus global TOA? What radiative feedbacks are responsible for the particularly low global feedbacks associated with this high latitude warmings captured by the first two patterns? So just as a bit of context, I want to show some results from this cool recent paper by Yue Dong et al. In 2019, where what Yue did was simulate the global climate response to patches of local warming using CAM5. So basically increase SST in each one of these patches and look at how the global climate responds. And in particular, the global mean top of atmosphere energy imbalance. And the result of that is this plot here, which shows the global mean radiative response to a local warming. So this shows that if you warm within this big blue region within the tropical Pacific warm pool, that you'll have a large negative response that damps this warming. So you warm in this region and you have a lot of energy loss over the whole globe. And this is a negative feedback that prevents this from having a big impact on global mean surface temperature, versus if you warm in any of these regions that are white or red, this is a weak global radiative response in these regions that would then allow you to have a big impact on global mean surface temperature. So what I'm doing here is instead of looking at these local SST anomalies, I'm using these modes of variability as a pattern to probe the global radiative response to warming in different regions. So first, I'm going to look at the first low frequency pattern that's capturing Atlantic multidecadal variability. And all the rest of these plots are going to stay the same for the next few slides. So this plot here is showing the evolution of global mean energy fluxes over time throughout the course of an AMV event. So this weak TOA is basically the result of canceling shortwave and longwave radiative feedbacks. And within the 10 years around the maximum, these shortwave and longwave feedbacks are shown in the map plots here. So the longwave feedbacks are basically acting to damp the warming. Everywhere that is warming has a increased outgoing longwave radiation. But what cancels that out is shortwave feedbacks due to reduction in sea ice and cloud cover. So basically positive sea ice albedo and cloud short and low cloud feedbacks cancel out the long wave cooling such that you have a weak overall feedback. Not a huge part of the story here, but the ocean heat uptake is basically just mirroring what's happening with TOA and the global mean, but it's really just happening in the action region of these modes of variability. And in particular, the spatial pattern here shows ocean heat loss in regions of warm SSTs, which is one way you can argue for the role of ocean circulations and ocean heat transport in this variability. So the story is pretty similar for the second pattern. You have weak TOA, net TOA, because of the canceling effects of long wave and short wave radiation. And the increased OLR in regions of warm temperature is again canceled out here mostly by positive sea ice albedo feedbacks. So you have sea ice loss as the ocean warms this region, and that amplifies this variability. And the ocean heat uptake again is occurring in regions of warm SSTs, indicating the role of ocean circulations and ocean heat transport. The story for the Pacific decadal variability is a little bit more complicated because near lag zero, you do have the long wave and short wave reinforcing each other. And this allows a larger but short-lived damping TOA radiated feedback that helps the PDO transition from this phase where it's having a positive influence on global mean surface temperature to this phase where it's having a negative influence on global mean surface temperature. But on the longer timescales, the long wave and short wave are canceling similar to how they did in the first two modes. So this makes its impact on radiation on decadal and longer timescales still quite weak. And this has a more complicated spatial pattern, which I don't want to discuss in too much detail, but you can see some evidence of this horseshoe pattern of the PDO within the shortwave feedbacks as well. And again, the pattern of ocean heat uptake here, our heat gain in regions of cold temperature shows a role of ocean heat transport and ocean circulations in this variability. For contrast, I'm showing the global energy budget change associated with ENSO here. So there's a little bit more going on here. So I'll take the time to take you through all these different figures. Basically, what I've done here is instead of just showing the anomalies for the 10 years surrounding lag zero, I've broken this up to focus on the kind of shorter timescales of ENSO into the year before the ENSO maximum and the year after the ENSO maximum. And that has slightly different SST patterns associated with it and correspondingly different radiated feedbacks. So in the period before, the long wave and short wave are reinforcing each other to give a net energy gain by the Earth system. And in the period after, they're reinforcing each other to give a net energy loss from the Earth system. And basically, where that's happening, if you look at the spatial maps, is in the period leading up to an ENSO maximum, the long wave and short wave feedbacks are reinforcing each other in the Eastern tropical Pacific, leading to positive feedbacks there that amplify ENSO. And in the period of ENSO decay, these subtropical regions are losing energy to space due to a combination of long wave damping as well as cloud feedbacks in the short wave. So that was all for that section of the talk, and kind of just want to summarize that by relating this back to kind of some more general principles of how decadal variability works in a climate system. So if you look at just a map of where pre-industrial control runs have interdecadal temperature variance, you'll see that it's really concentrated in the high latitude regions and avoids these regions of tropical deep convection. So you really don't have decadal temperature variability in these regions. So these high latitude regions that have a lot of interdecadal variability are these regions I talked about that have these weak radiative feedbacks because of the cancellation between shortwave sea ice and cloud albedo feedbacks and long wave radiation. Whereas these tropical regions that have a very large impact on global radiation, as showed also by Yue Dong's work, don't have much interdecadal temperature variability. And I would argue that this is actually there's actual causal reason for this, because if you have such a strong damping mechanism for your variability in these regions, it can't persist for the decadal and longer timescales. Where if you just have temperature anomalies in these high latitude regions, there's no radiative feedbacks to damp them. There's also inefficient heat transport out of this region. So then these anomalies can persist for long timescales. And just to reinforce this, if you do compare the interdecadal temperature variability between forced historical simulations and pre-industrial control, look at the same metric, the change in the same metric, you'll see that all of these tropical deep convection regions do then have interdecadal temperature variability. It just requires some sort of external forcing to change global mean TOA and allow variability in these regions. So finally, want to talk about how all of this adds up to influence estimates of climate sensitivity from short observational periods. So to go back to this inferred climate sensitivity equation, and in particular, this separation into forced and unforced components that I showed before. And basically what I'm going to be doing within these pre-industrial control simulations is specifying representative values for the forced response, and then just plugging in the internal variability in global mean temperature and global mean TOA into these internal components, and then computing how the spread of ICS results from different modes of low frequency variability in the CMIP6 pre-industrial control simulations. So first, I just want to show what the total spread would look like by doing this procedure, plugging the CMIP6 pre-industrial control simulations into this equation with a assumed value of the forced response. And the X and Y axes on these plots are just showing the assumed value of the forced response, how much historical warming has occurred, and what is the radiative response to that warming in terms of an effective climate sensitivity. And I'm showing this for both inferred climate sensitivity based on 10-year averages and based on 30-year averages. And what's shown in the contours then is the 95% spread in ICS that you'd expect from the internal variability. So all kinds of internal variability here. And so that's plus or minus 0.65 degrees C for a 10-year average, or 0.36 for a 30-year average. So this is this spread in this plot that I showed earlier. And it is sensitive, of course, to the amount of forced response that has occurred, which is what the axes are showing. And so the modes of variability I've been talking about in the high latitude oceans are really mostly explaining global mean surface temperature variability, not TOA. So I want to know also how much of this ICS spread is simply just due to the decadal variability in global mean surface temperature. And it's not all of it, but it's a substantial fraction of it. So 0.36 compared to 0.65 at this reference value I'm showing. But at 30-year and longer timescales, it's really a much larger fraction of this. So the longer timescales you go to, it's really this global mean surface temperature variability that matters for the spread in ICS, not the TOA. Now in these somewhat complicated plots that I'll try to walk you through. I'm going to split this spread in ICS into different modes of variability. So what each of these plots are showing for the different modes of variability is the contemporaneous impact of this mode of variability on global mean TOA and global mean temperature on the y and x-axis respectively. And then the diagonal lines show how this turns into an impact on inferred climate sensitivity. So these first two low frequency components that have a big impact on global mean surface temperature, shown on the y-axis, influence ICS primarily through this impact on global mean surface temperature. And this, of course, depends a lot across the models. And the models that have the biggest impact on ICS of these different modes are the ones that have the really large amplitudes of these modes that I already pointed out earlier in the talk. So EC Earth and IPSL for the Atlantic multidecadal variability, and BCC and GFDL for the Southern Ocean multidecadal variability. But even the more average model still has an impact on ICS spread of plus or minus 0.2 from A and B, plus or minus 0.2 degrees C from Southern Ocean multidecadal variability. PDO and El Nino don't really have a strong contemporaneous impact on global mean surface temperature or TOA. What they have instead is an impact on the difference between the 5 years after them and the 5 years before them. So that's what I'm showing here in this plot. So don't worry too much about what the first two show. I'm going to focus mostly on what the PDO and ENSO show here. PDO, it has influences a large change in global mean surface temperature between the 5 years after and 5 years before. So this is a negative value on the x-axis here. So it's a reduction in the rate of warming. But it has some compensating feedback, so it doesn't actually end up influencing ICS very much in this way. El Nino, on the other hand, has such a huge impact on the change in TOA between the 5 years after and the 5 years before that this amounts to a very large impact on inferred climate sensitivity. And so just to kind of think a little bit more about why, how is this happening and how to avoid this in some decadal period that we choose to infer climate sensitivity from, just kind of throwing the Nino 3.4 record up here and gonna take out some snapshots of this and talk about how the ICS would be influenced in these different periods. So if we look at a recent period here that has pretty neutral ENSO conditions and is roughly corresponding to the hiatus period or the later part of the hiatus period, this could be problematic if you get too close to this 2015-16 El Nino, because even if there's not yet an El Nino occurring according to the Nino 3.4 index, you could still be incorporating some of this ocean heat content and top of atmosphere energy imbalance buildup that's leading up to this ENSO event. The really most problematic time periods to choose would be one that has a trend in ENSO, so goes from well, either direction, but in this case from a La Nina to an El Nino, where it basically combines the heat gain that happens after a La Nina event with the heat gain that happens leading up to an ENSO event, such that you have this huge amount of heat gain over this period, corresponding to a large top of atmosphere energy imbalance. Really, what you want to choose is something that has neutral ENSO conditions in a couple years surrounding the edges of your time period. No matter what's going on in the middle, it's really what's happening at the edges that makes the biggest difference. Because you want to capture all of the radiative impacts associated with ENSO, both the buildup and decay phases. So in summary, the low frequency pattern 1 and low frequency pattern 2 influence ICS through their large impact on global mean surface temperature. If the period used is biased towards one phase or the other of these modes of variability. ENSO, and also to a lesser extent the PDO, influence ICS. On the other hand, if the period used doesn't include all of the lead and lag impacts on TOA and global temperature. So there it's more important that you capture full ENSO events and don't have ENSO events on the edges of your time period used to infer climate sensitivity. So to summarize across the whole talk, in pre-industrial control simulations, GMST variability is dominated by variability in the high latitude oceans through modes of variability such as the AMV and the Southern Ocean multi-decadal variability. These regions have weak radiative feedbacks due to positive shortwave sea ice and cloud albedo feedbacks that cancel the negative OLR feedback. Variability in the tropics that would trigger anomalies in tropical deep convection would have a very large impact on the global energy budget. So it generally does not just simply doesn't occur on these decadal timescales because this would require a huge source of energy to sustain it. And if you infer climate sensitivity from historical anomalies, it can be biased from either of these types of variability, both from the global temperature impacts of the multidecadal variability or from the TOA impacts either of ENSO or of shorter timescale white noise. I don't think this quite gives you the framework that we need to really interpret what's going on in the historical record, but I do want to at least highlight one of the main open questions we have in order to be able to apply this to the historical record. And that is, as I highlighted in the introduction, is the weird pattern of SST anomalies that has happened over the last 40 years forced or unforced. So another way of showing this, I've put the SST trend in terms of standard deviations within the CSM large ensemble away from the CSM large ensemble mean. So this really highlights how unusual this SST pattern change is, with 2 to 3 standard deviation anomalies in many places and as much as 6 in some regions of the Southern Ocean and North Atlantic. So this kind of hints that there is at least some large bias in the forced response, but it does seem like, based on work by Lapelle and Hubers and a lot more recent work, that there is maybe too little multidecadal variability in tropical and subtropical SSTs and models. So understanding what is the source of why something like the CSM large ensemble can't simulate this unusual of a warming pattern with its unusual impacts on global TOA radiation requires looking into both the forced response biases and the biases in the internal variability. So that's all I have. This is work soon to be submitted to the Journal of Climate, and I also highlighted this paper by Luke Parsons, and I'd like to thank my collaborators and funding, and I'm happy to take questions. Thank you.
Thanks very much, Rob. Very interesting talk. We do have a couple minutes for questions. If you have a question for Rob, you can use the raise your hand feature, which is in the participants window, and ask your question out loud, or if you prefer, you can type your question in the chat. So we already have a question from Clara. Go ahead.
Hi, Rob. Thank you so much for such an excellent talk. I learned a lot, as I always do, from you. I just had a few questions. You never showed air temperature over land, and of course that affects the GMST. So I wondered if you had any comments about how your low frequency patterns, how they are expressed in land air temperature. And then I was just wondering also about when you talk about ENSO impacts, are you just talking about this, the sampling of the interannual ENSO, and that's leading to these impacts on the decadal and longer time scales, or are you talking about some slower modulation of ENSO? I just wanted some clarification. Thanks.
Yeah, great questions. So on about the surface air temperature impacts, there's definitely warming in the surrounding continental regions associated with each of these modes of variability. That's larger than the SST impacts actually, but it's localized to the continental regions that immediately border the ocean basins that the modes of variability are occurring in. And actually one of the big ways that these modes of variability impact global mean surface temperature is if they cause sea ice anomalies, because that has a very large impact on surface air temperature as you move from a ice-covered region to the warm ocean underneath. Then on the sampling versus low frequency modulation of ENSO, so I'm mostly thinking about it as a sampling of the interannual ENSO, but there's a little bit of both. So easier to access this extra slide here, just showing the bottom two left panels here, which is what I showed in the talk. I showed the impact of Nino 3.4 on GMST and global mean TOA in the black line, but there's also a representation of ENSO within this low frequency component analysis in the least low frequency component, which I didn't talk about, and that's the dashed line here. And here, that's really the interannual ENSO, and its impact on decadal and longer timescales really dies out a bit. So there is some part of the ENSO impact on global climate that's coming from this decadal modulation of ENSO, but that's already partly captured by the other modes of variability like the PDO. So partly that's coming through the PDO.
Thank you.
Isla has a question.
Yep, thanks for the great talk. I was just wondering if you've thought about the intermodal differences in the low frequency variability and whether you've looked into whether the different radiative feedbacks might play a role, or is it all just differences in the nature of the ocean variability?
I've been thinking of it as differences in the ocean variability, but I don't know if I have a way to demonstrate that conclusively, because basically the models that have the largest variability in the AMV or the Southern Ocean multidecadal variability are also having the largest, well, okay, no, they don't really have large TOA impacts. They just have large GMST impacts. So I think this really has to do with the ocean, because these modes already don't have much radiative feedbacks associated with them. So I wouldn't think that's what's influencing why they have the amplitudes of variability that they do. If you start to talk about other variability, like anything involving the tropics a bit more, then it might make more of a difference what the radiative feedbacks say about how much variability you can have in those regions.
Okay, thanks.
Any other questions for Rob? Isla, is that another question, or did you?
Yeah, I did have another question if no one else has one.
Yeah, go ahead.
I came in a bit late, so maybe I missed this, but I was just wondering if you could comment on how correlated your AMV is with traditional indices of the AMV, and whether we should be still using those indices, or if you think this one is more physical.
Yeah, so this particular one, which was defined based on global SSTs, a pattern of global SSTs, was 90% coherent with the traditional AMV at decadal and longer timescales. So it's basically capturing the same decadal variability. But if you limit the domain of your analysis to the Atlantic basin, that will increase even further to some 95, 96% coherence with the AMV. And I think that does make this a very good way to define the AMV that focuses on the regions that are really relevant on the decadal and longer timescales, while still capturing the same decadal variability of traditional indices.
Thanks.
Great. Well, I'm not seeing any other questions. We're at the top of the hour, so I think we'll close. Thank you again, Rob, for a really nice talk. And next week, we will hear from